So how many of you guys have taken Gen Chem within the last year? Exactly, and that's the problem here on this section, right? It's all going back to Gen Chem, acids, bases, buffers. So that's the unfortunate part, so we gotta get you caught up to speed. So acids and bases. We are only going to use one of the definitions you learned back in the day. You would have learned three. You would have learned the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. We're only using Bronsted-Lowry. What's Bronsted-Lowry's definition of an acid? Good, proton donor. Somebody name for me a good example of, or the most famous example, how's that? HCl, by far, the most famous example of a proton donor. So, and therefore the definition of base? Cool, and this is the only definition we're pretty much going to look at in a biochemistry context, Bronsted and Lowry's definition here. Now, what do I mean when I say proton? So, because often can be a little bit deceptive. I don't just mean like the little tiny particle, that we call a proton that's in a nucleus, although yes, I do in fact as well. So, but I don't want you to think of it that way. A proton is simply an H plus ion. That's what we're talking about. Notice hydrogen has one proton, one electron. So if I lose that electron, I'll have a plus charge. And so the only thing that's left is just simply a proton. And so really we're talking about hydrogen ion donors and hydrogen ion acceptors here when we talk about acids and bases. But I'll call it proton most of the time. I just want you to realize that don't think of like super subatomic particle in the nucleus, even though that's what it is. But think about hydrogen ions is what we're really talking about. All right, so we got to go over some really old school definitions of some calculations we'll do. pH, what does pH mean? Negative log of H plus. What does pOH mean? Cool, negative log of OH minus. What does pKa mean? Negative log of Ka. So what does P mean? Negative log. So in this case, P of whatever you do is the negative log of something. P is a mathematical function here in this case, in this context. So in this case, so pH is negative log of H plus. If I knew the H plus, let's say in pure water at 25 degrees Celsius, the H plus is 10 to the negative 7 molar. Okay, if the H plus in pure water is 10 to the negative 7 molar, then what's the pH? 7. Because the negative log of 10 to the negative 7 is 7. That's where that comes from. Now, if we rearrange this, we can go backwards with this too. In fact, let's do this in a separate color. We can go backwards with this. If I want to solve for H plus, so the math here gets to be a little bit of the parts of algebra in high school that you forgot. So, but here, to solve for H plus, I got to get the log term by itself. So I'll bring the negative to the other side and have negative pH. And then to get rid of a log, it's 10 to the power of. That's what the antilog is. And so that's why in this case, it's 10 to the negative pH. 10 to the power of log cancels, but 10 to the, brought the negative over, 10 to the negative pH is what you have on the other side. That's where that comes from. So the more you understand how to rearrange these equations, the fewer equations you actually have to know. Same thing with the OH minus. It's 10 to the negative POH. Same thing with the Ka. Ka is 10 to the negative pKa. Cool. Are we going to talk about Kas or pKas more in this class? We'll talk about pKas more. So a couple key places where we'll have to remember what Ka is, though. It'll be more important to use that particular form. Cool. Some other little reminders here. So we've got pH, POH, H plus, and OH minus. All four of those are mathematically related to each other. So, and if we look, we can kind of see why. If you look at water, if I have pure water, I got a bottle of water sitting right over there. If I have pure water, how much dog hair do you suppose is in there? I would hope none. It's pure water, right? So how much coffee is in there? I would still hope none. So how much of anything other than water is in there? Well, you'd hope none, but you'd be wrong. Because pure water has a little bit of something that's not water. In this case, it has a little bit of H plus and a little bit of OH minus. It's inherent. So it turns out you can't have water without having these in it. Water dissociates, we say autoionizes, just to a very small extent into H plus and OH minus. And if you look at the equilibrium constant for this process, first we call that equilibrium constant Kw, and the expression is H plus times OH minus. Notice, why doesn't water show up in this expression? It's a liquid. Liquids have an activity of 1, and we just leave them out. No solids, no liquids. So when it turns out at 25 degrees Celsius, this is equal to 10 to the negative 14. So notice, in Gen Chem, the only temperature you ever would have considered is 25 degrees Celsius. Now, in biochemistry, is that the only temperature we're ever going to consider? So in a grander sense, no. For acid-base stuff, probably, unless specified otherwise, just assume 25 degrees Celsius. Although, what's a more relevant temperature if you're talking about human biochemistry? 37 degrees Celsius. So even though this is what we'll always use, and probably always use in this class even, so keep in mind, if you actually started working in a lab sometime, you might switch temperatures, and this number might change just a little bit differently. So if you're working at 37 degrees Celsius. Cool. So, but it's from this equation where we get pH plus POH also adding up to 14. If you take the negative log of this whole equation, that's what you get. Okay, so here's the deal again. pH, POH, H plus, OH minus, because of Kw here, the autoionization of water, these are all mathematical functions of each other, all 4 of them. What that means is if you know any one of these 4, you know all 4. Or at least you should be able to calculate the other 3. So let's say I told you that the pH in the body was 7.4. pH in your blood, say, is 7.4. Well, what's the POH in your blood? What is it? Good, 6.6, assuming your blood is at 25 degrees Celsius, right? But anyways, yeah, 6.6. They have to add up to 14. If you knew pH, you automatically know POH. But if you know pH, you should also know the H plus concentration. What is the H plus concentration? 10 to the negative what? 7.4, sweet. So can I write that like that? Well, I just did, so obviously I can. But so is this proper? It's not proper. Can you write it like this? You can write it like this all day long. Now, if you were looking for that answer choice on your test, you're not going to find it. But just plug that into your calculator and let your calculator tell you what it looks like proper. But if you're just making notes and doing a little bit of, working out, setting up the problem in your head and stuff like that, by all means, just write that. So, but again, if you're looking for the answer choice, put it in your calculator. Let it tell you what it is. Same reasoning, hydroxide. What's going to be the hydroxide concentration? That's in molarity, by the way. What's the hydroxide concentration going to be in this case? Awesome, 10 to the negative 6.6 molar. Cool. The only thing I gave you was pH. By giving you pH, we got the other 3. They're all functions of each other. You know one, you should be able to get all the other 3. So the little chart, the diagram on your handout, kind of shows you how to get around the horn from pH to H plus to POH to OH minus, depending on where you are. So if you need some help with that, I highly recommend just working a few examples using that chart to refresh it back in your head. So HCl, most famous acid of all time. Where do you find it? In your tummy. Where else? Probably have one of these at home in all likelihood at some point in your life in Arizona. Your pool. You pour it in your pool. So notice, do they call it hydrochloric acid on the bottle? No, what do they call it? Muriatic acid. Why do they do that? I don't really know why they do it. I'm just thinking that they get some biochemistry students like looking at it and be like, oh, that's hydrochloric acid. It's the same stuff in my tummy. Bottoms up. So the stuff that you pour in your pool is way more concentrated than what's in your tummy, just FYI, but it's the same stuff, hydrochloric acid. So most famous acid of all time, and what kind of acid is it? Strong acid. What does that mean? Dissociates how much? Fully, completely. Is that really true? No, it's actually not really true. It's just almost true. So it turns out it dissociates like 99.9999% or something like that, so we just round it up to 100. So no acid actually dissociates 100%. So, but the strong acids come so close that we just round it up. So the definition we will use for strong acids in this class is that they dissociate fully. It's one you used in Gen Chem back in the day and stuff as well. But just keep in mind, it's an oversimplification. It's not quite completely true. So, but here's a strong acid. If I had, you know, say, where's the question on your handout there? 0.01 molar HCl. My question then is, what is the H plus concentration in that solution? 0.01. It's a 1-to-1 ratio. For every HCl that dissociates, and they all do, you get an H plus. And so if it's 0.01 molar HCl, then it's 0.01 molar H plus. And if it's 0.01 molar H plus, what's the pH? It's 2. How did I get that? Well, what is the definition of pH? Negative log of that. Negative log of H plus. So I just took the negative log of 0.01. 0.01 is the same as 10 to the negative 2. If you take the negative log of that, that's why you get 2. So it was a nice round number. Had I not given you a nice round number, I would have needed a little help from your calculator as well. Cool, but what if I have, and actually let's make it 0.1 molar acetic acid. Now, where do you find acetic acid? Vinegar. So principal acid component in vinegar. So it looks like this. If I have 0.1 molar acetic acid, what's the H plus concentration? That was exactly the answer I was looking for. No, that's actually, we don't know. So acetic acid is not a strong acid, which is good, right? If it was a strong acid, you wouldn't want to put that in your salad dressing. So it's not a strong acid. And so I don't know what the H plus is, but I know what the H plus isn't. What is the H plus not equal to? It is not 0.1 molar. What is the pH also not equal to? 1. If this were strong, the H plus would have been 0.1. And the pH would have been 1, but it's not strong. And so your H plus is not going to be this high, and your pH is not going to be this low. Cool. But it's not a problem I can solve unless I give you a little more information. So for acetic acid, we can talk about the same kind of dissociation we did with HCl. Except it's an equilibrium dissociation now. I mean, technically it really was an equilibrium. It's not 100%, but again, we pretended that it was. But here it's not even close to 100%. In fact, for a weak acid, it's usually a lot less than 100%. A lot less than 50% is pretty typical. A lot less than 5% is actually even pretty typical. So only partially dissociate here. So, and by getting an equilibrium constant for this process, in this case, the equilibrium constant Ka for acetic acid is 1.8 times 10 to the minus 5. We can look those up in tables. Could have also told you that maybe the pKa was 4.75. If I'm going to give you only one of these two, which of these two am I probably more likely to give you? Probably going to give you the pKa. So unfortunately, for just a simple weak acid problem, I can't calculate the pH very easily with just a pKa. I need the Ka. So in this case, the Ka is just the equilibrium constant of this reaction. That's H plus times C2H3O2 minus, the conjugate base of acetic acid, the acetate ion, all over cool. And in this case, if we look at this dissociation, if I told you this reaction happened 10 times on the way to equilibrium, how many H pluses would you form? 10. How many acetates would you form? 10. Cool. I don't know if this happens 10 times. If I told you it happened 100 times, how many H pluses would you get? 100. How many acetates? 100. Well, here's the deal. We don't know how many times this happens before it reaches equilibrium, so to speak. So we just say it happens X number of times. If it happens X number of times, what concentration of H plus do you get? X. Sweet. What concentration of acetate do you get? X. And if you started out with a 0.1 molar solution of acetic acid, how much will be left after this reaction happens x times? 0.1 minus x. Every time it happens, I lose 1. So if it happens x times, I lose x amount. That was essentially those ice tables you did in Gen Chem, right? Cool. In this case, you just set this equal to the Ka, and you solve for x, keeping in mind that x was your H plus concentration, and that's your key to getting the pH in this case. And again, the pH is not going to come out to 1. Your H plus is not going to come out to 0.1. So it's going to be some other number here. So what is the most mathematically sound way of solving this expression when it's equal to 1.8 times 10 to the minus 5? Quadratic equation. Oh, isn't that fun? Are we using the quadratic equation here? No, not at all. So when you see an equilibrium constant that's really small, that tells you that the reaction favors what? The reactants. And if the reaction favors the reactants, well, initially, all I had was just the reactant. And when we're done, we're going to have mostly only reactants, which means x, the number of times that this happens, must be small. And that's the key here. What's 0.1 minus a really small number? It's 0.1. You know, 0.1 minus 0.00001 would just be simply 0.1. I mean, it'd really be 0.099999, you know. But it's 0.1 for all intents and purposes. And we're just going to ignore that. Notice, if you multiply by a small number, is that still an insignificant result? No, that's significant. Notice if you take and subtract off 1/1,000,000th of a dollar out of Bill Gates' bank account, will he notice? If you added 1/1,000,000th of a dollar, would he notice? No. If you multiplied the value of his bank account by 1/1,000,000th, would he notice? Yeah, you better believe it. You take his $1 billion bank account, and it would now be worth $1,000. I think he's going to be a little ticked. So notice when you multiply by a small number, it has a huge impact. You can't ignore those. It's only when you add it or subtract it, so he's gone. So in this case, we're going to be left with x squared over 0.1 equals 1.8 times 10 to the negative 5, or x squared equals 1.8 times 10 to the negative 6. Take the square root. X equals 1.3 times 10 to the negative 3. And in this case, x was equal to what, though? That's allowing us to get pH? The H plus concentration. So this is your H plus concentration. And we can see, yeah, the H plus was definitely not equal to 0.1. It was equal to something substantially smaller, only dissociated partially. And in this case, what does that get you for a pH? If you work it out, it should be somewhere right around 2.9. Cool, just took the negative log of this number. So we see, yeah, the pH was definitely not equal to 1. It was quite a bit higher. Cool. So this is kind of the general approach we take for just simply having a weak acid in our solution. We take a very similar approach to just simply having a weak base in the solution. But if it were a weak base, what would we need instead of Ka? Kb. And we wouldn't be solving for H+, we'd be solving for OH-.